Today, a sliver of silicon, no larger than a fingernail, can compose poetry, generate photorealistic art, solve complex quantum equations, and reason across dozens of human languages. Yet, silicon is nothing more than refined, melted sand. How did humanity teach lifeless, inanimate mineral grains to think, to reason, and to learn from their own mistakes? To truly understand modern artificial intelligence, we must zoom out and witness the complete 70-year intellectual journey, a dramatic story of grand ambitions, devastating collapses, and breathtaking resurrections. Across this epic timeline, 4 foundational pillars of modern intelligence were born: artificial intelligence, machine learning, deep learning, and reinforcement learning. Our story begins in 1950 with the father of computer science, Alan Turing. In his landmark paper, Computing Machinery and Intelligence, Turing posed a deceptively simple question: can machines think? He introduced the famous Turing test. 6 years later, at the legendary 1956 Dartmouth Summer Workshop, brilliant minds including John McCarthy, Marvin Minsky, and Claude Shannon officially coined the term artificial intelligence. In those early days, intelligence was believed to be pure symbolic logic. Under this symbolic AI paradigm, scientists believed that human reasoning could be captured entirely by handwritten rules and nested if-then statements. The assumption was straightforward: if we hand-code every rule of grammar, physics, and logic, machines will become intelligent. But the real world proved far too noisy, chaotic, and ambiguous to ever fit inside handwritten code. The revolutionary paradigm shift arrived in 1958 with psychologist Frank Rosenblatt. Rosenblatt realized something profound. We should not write rules for the machine. We must build a system that learns its own rules directly from data. This marked the birth of machine learning. Inspired by biological neurons in the human brain, Rosenblatt unveiled the Mark I Perceptron. The Perceptron was an elegant mathematical formula. It takes inputs, multiplies each by a numerical weight, adds a bias value, and fires a positive signal if the sum surpasses 0. Geometrically, this single artificial neuron draws a straight, flat decision boundary through space to separate 2 categories of data. Rosenblatt famously claimed that the perceptron would soon walk, talk, and become self-aware. But he overlooked a fatal mathematical limitation lurking in the shadows. In 1969, MIT computer science pioneers Marvin Minsky and Seymour Papert published their devastating book, simply titled Perceptrons. Inside, they delivered a rigorous mathematical proof that shocked the world. A single-layer perceptron could not even solve the most basic logic operation in computer science, the XOR, or exclusive OR function. In an XOR problem, data points are arranged diagonally across a 2-dimensional grid. No single straight line in mathematics can ever separate them. The fallout was catastrophic. Funding agencies, including DARPA, felt deeply misled and pulled millions of dollars in research grants overnight. AI laboratories shuttered their doors. This marked the arrival of the first AI winter, a dark 15-year intellectual freeze where researching neural networks was treated as academic career suicide. Yet in the quiet shadows of this winter, a handful of visionary researchers refused to surrender. Among them were Geoffrey Hinton, Yann LeCun, and Yoshua Bengio. They recognized that while a single neuron draws only a straight line, stacking multiple hidden layers of neurons could warp, twist, and bend multidimensional space, enabling the network to solve nonlinear problems like XOR with effortless grace. This was the birth of deep learning. However, a monumental puzzle remained. In a network containing thousands or millions of interconnected weights, How do you mathematically adjust every single weight so the entire network reaches the correct answer? The answer arrived in 1986 in a groundbreaking Nature paper by David Rumelhart, Geoffrey Hinton, and Ronald Williams. Backpropagation. Using the chain rule of calculus, the system calculates the error at the final output and propagates that error backward through every layer of the network. Each weight is adjusted along the negative slope of its error function, a process known as gradient descent. Imagine a hiker lost in thick fog atop a rugged mountain range. By feeling the steepness of the terrain beneath their feet, they take step-by-step descents toward the lowest valley of minimum error. In 1998, Jan LeCun published his historic LeNet 5 architecture, demonstrating that convolutional neural networks, or CNNs, could scan spatial pixel grids like an artificial eye and read human handwriting on bank checks with superhuman precision. The mathematics of deep learning was finally complete. Yet the world lacked two vital ingredients: massive datasets and raw computational horsepower. The ultimate ignition point erupted in 2012 at the ImageNet Visual Recognition Challenge. Stanford professor Fei-Fei Li had spent years assembling ImageNet, a monumental dataset containing 14 million labeled images. That autumn, Alex Krzyzewski and Ilya Sutskever, supervised by Geoffrey Hinton, unleashed AlexNet. Their stroke of genius was implementing deep convolutional networks on NVIDIA GPU graphics cards, originally engineered for rendering 3D video games, which happened to be exceptionally fast at parallel matrix multiplication. AlexNet crushed the competition, slashing visual error rates in half overnight. The modern deep learning revolution had officially exploded into the mainstream. Simultaneously, another grand pillar of intelligence was quietly maturing based on the foundational theories of Richard Sutton and Andrew Barto: reinforcement learning. Unlike supervised learning, which requires millions of labeled examples, reinforcement learning functions like a child exploring a playground. An autonomous agent interacts with an environment, learning purely through trial, error, reward, and punishment. In 2016, Demis Hassabis and David Silver at Google DeepMind unveiled AlphaGo. Combining deep neural networks with reinforcement learning and tree search, AlphaGo defeated 18-time world champion Lee Sedol in the ancient game of Go, executing legendary moves that no human master had ever conceived in 2,500 years of history. Despite these staggering visual and strategic victories, human language remained a formidable frontier. Earlier language models relied on recurrent neural networks, reading sentences sequentially, word by word. As sentences grew longer, these networks suffered from computational amnesia, losing context and taking weeks to train. Then, in 2017, an 8-person research team at Google published a landmark paper with a daring title: "Attention is all you need." They introduced the transformer architecture and the revolutionary concept of self-attention. Instead of processing words one at a time, a transformer ingests entire documents simultaneously in parallel. Through 3 learned mathematical representations, queries, keys, and values, every single word dynamically computes its contextual relevance to every other word in a high-dimensional vector space. The transformer unlocked unprecedented scaling laws. When fed terabytes of internet text and trained across tens of thousands of GPU clusters, these models developed emergent reasoning capabilities, giving rise to OpenAI's GPT series, Anthropic's Claude, Google's Gemini, and the generative AI renaissance we witness today. Yet the ultimate ambition of artificial intelligence extends beyond generating text and pixels on digital screens. It is about stepping into the physical world, a frontier known as embodied AI. For decades, creating a bipedal robot capable of navigating complex physical environments was considered nearly impossible using conventional control algorithms. Pioneering robotics leaders like Boston Dynamics revolutionized physical locomotion by deploying deep reinforcement learning inside high-fidelity physics simulators. Humanoid robots like Atlas performed millions of simulated trials in virtual space, falling, slipping, and correcting their balance billions of times per second. Through continuous policy optimization, these artificial brains learned to master dynamic athletic balance, performing parkour, executing flawless backflips, navigating treacherous icy terrain, and manipulating heavy industrial objects with millisecond hydraulic precision. Today, as multimodal vision-language-action foundation models merge with advanced robotic bodies, the boundary between digital thought and physical action is dissolving. From Alan Turing's theoretical musings in 1950 and Frank Rosenblatt's Room Full of Wires, to Geoffrey Hinton's gradient valleys, AlphaGo's brilliant intuition, and humanoid robots moving through our physical world, we have spent 7 decades teaching lifeless silicon and electricity to experience, to adapt, and to understand. This is not the final chapter in the history of artificial intelligence. It is merely the end of its prologue.